All right, this is problem 2 from paper 3 from November 2014. It's a 14-mark question. Part A says use the integrating factor to show the general solution for, and this is the, right there. That's a differential equation we're trying to solve, and it gives us the answer, which I won't go ahead and tell you yet. But let's review integrating factor. In order to use the integrating factor method, the differential equation must be in this form. So this problem's a little tricky because they switch up the variables on us. Well, it is in that form, but instead of y, we've got x, and then instead of x, we've got t. So it's a function of x and t. So let's kind of play around with this equation a little bit. The second part of the integrating factor requirement is you have a function of x, in other words, the bottom variable, times y, the top variable. Well, in our problem, the top variable is x. So the function of the bottom variable, t, would be 1 over t. So we're going to separate that. And then on the right-hand side, you have a function of x, which is the bottom variable. So we have a function of t. So everything is set up correctly. Now the integrating factor, you find that and you multiply this differential equation. Every single term we're going to multiply by the integrating factor. And the integrating factor is always e to the integral of the px function. That's the function that we just separated out. So that's your negative 1 over t. So we're going to fill that in. So if we do the exponent part of this, the integral of negative 1 over t is the same as negative integral of 1 over t. And the integral of 1 over t is ln t. So it's e to the negative ln t. And we're going to use a logarithm property. If you have a negative out front, we're going to take it in as the power. So it's e to the ln t to the negative 1. Now, a property of e and ln is that e to the ln of anything is just this thing. So this is equal to t to the negative 1, which is 1 over t. So that's our integrating factor. So we're going to go back to our differential equation and multiply everything by 1 over t. So 1 over t dx dt minus 1 over t times the 1 over t that was already there, times x equals negative 2 over t times 1 over t. Okay, let me clean that up a little bit. Multiply those t's together, so we have 1 over t dx dt minus 1 over t squared times x equals negative 2 over t squared. All right, then after you multiply through by the integrating factor, you integrate both sides. Now here's the one little tricky part. Remember, the left-hand side is the result of the product rule. You're going backwards. So after you integrate this side, and you can always check this, you're going to get the result of the integrating factor times that top variable. Usually it's a y, but in our case it's an x. So the integrating factor was 1 over t, and that top variable is x. So that's the result. Now, as I said, you could double check that, take the derivative of this thing, first derivative second, second derivative first, and you're going to get what's inside that integral. Now on the right hand side, when we differentiate that, we get negative 2, which we can kick out front, and then we got 1 over t squared, so we increase that negative 2 power to a negative 1, so it's going to be 1 over t to the first, and that negative 1 goes to the bottom, so all that's going to do is change the sign. So the result of integrating both sides, we have x over t on the left equals 2 over t on the right, and don't forget plus c. Now, if you take that equation and multiply through by t, you get x equals 2 plus ct. And that is exactly what they told us the answer had to be. So it said use the integrating factor to show that the general solution is x equals 2 plus ct. So that part is done. So integrating factor, it is on your formula sheet. if you can remember how to go through the process. As I said, this one was a little confusing because of the t's and the x's being interchanged and not in the normal form. All right, now we're ready for part B. So let me scroll up here a little bit. Part B, we're given a piecewise function. WT, which stands for weight, is 2 plus CT when t is between 0 and 5, inclusive. And the function is equal to 16 minus 35 over t when t is greater than 5. And what that is, W is the weight of a dog t weeks after being brought home from the pet shop. So the first part of B, or the first part of this scenario, says, given that WT is continuous, find the value of C. Now remember, if a piecewise function is continuous, then the two pieces will equal one another where the function breaks apart in the domain. So it breaks apart at 5, so it's 0 to 5, and then t is greater than 5. So you simply set the two pieces equal to each other and substitute in, I just see I made a mistake, that 6 up at the top piece should be that should be a t. There we go. You set the two pieces equal to each other, and for t you substitute in the number, the value where it breaks apart, which is 5. So 2 plus 5c equals 16 minus 35 over 5. 2 plus 5c equals 16 minus 7, which is 9. 5c equals 7. C equals 7/5. So the value of 7/5, if you put it back into the original piecewise function, will guarantee that that function is continuous. So part B is done. That was 2 marks. Part C is real easy. I'll just do it over here on the right. It says, write down the weight of the dog when bought from the pet shop. Well, when it's bought from the pet shop, that's the time is 0. That's the number of, I think it's weeks. Yeah, the number of weeks since the dog was bought. Well, at the pet shop, you just bought him, so no weeks have elapsed. You simply take the piecewise top piece, 2 plus CT, and C now is 7/5, times T, and you let T equal 0. So the weight of the dog initially is 2 pounds. Or it could be kilograms. Let me check my units. It is kg. Get that out of there. So that was easy. The next question for C says, find the upper bound for the weight of the dog. So as time goes by, as time keeps increasing, so what I'm going to do is take the limit as t goes to infinity and use the bottom piece of the piecewise, because infinity is definitely bigger than 5. 16 minus 35 t over t. As t goes to infinity, this fraction becomes extremely small, therefore approaching 0, and the value of this piecewise is 16 kilograms. So over the long haul, the dog will weigh about 16 kilograms. That's the upper end. So A, B, and C are done. Part D is a little messy. Let me get a blank page here. It says, prove from first principles that WT, the weight function, is differentiable. So what's that mean? Well, when you're talking about the differentiability of a piecewise, again, the two pieces, they have to, the derivative of the first piece has to equal the derivative of the second piece where they come together, or where they break apart, however you want to look at it. So at 5, the two derivatives have to be approaching each other. So we're going to take the derivative of the top piece, which was 2 plus 7/5 t, from 0 up to 5. And then the bottom piece was 16 minus 35 over t. Well, that's a funky t. Let me get that out of there. And that's when t is greater than 5. So we have to show that the derivatives of those two parts are going to equal each other when t is approaching 5 from the left and the right. Now, the tricky part of this, the messy part, is they don't want you to just take the derivatives. They want you to use first principles. Now, what first principles is, it's the definition of derivative. It's the first thing you learn when you learn to take derivatives. which is the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, you just apply that definition to each of the two pieces, sub in 5, and see if you get the same result. So it's just a lot of work. It's really not that difficult. So let's do the top piece using the definition. So it's going to be the limit as h approaches 0. F of x plus h will be the piecewise function, top piece, 2 plus 7/5 t plus h, minus f of x, or w of t, which is 2 plus 7/5 t, all over h. So the object here is to clean that up so we can take the limit as h approaches 0. Well, it's just a bunch of algebra, so we have the limit as h approaches 0, 2 plus 7/5 t plus 7/5 h, doing all that distribution, minus, now let me be careful here with our signs. I really should put that in parentheses. You're subtracting f of x, or you're subtracting w of t, so that makes it minus 2 minus 7/5 t all over h. Again, the goal here is to take that limit. So we're just cleaning this thing up, rewriting limit 100 times. So what happens? Let's see, the 7/5 t's cancel out, the 2's cancel out, and you're left with 7/5 h over h. The h's cancel out, so the limit as h approaches 0 is equal to 7/5. So the derivative of the first part as t gets closer and closer to 5 is going to be 7/5. And that's obvious anyway, because the top piece is linear. Think of y equals mx plus b. The slope is 7/5, therefore the derivative is equal to 7/5. But they made you go through all that work just to show that. All right, one more little piece, and that is we're going to use the definition of derivative, or first principles as it's known as, on the bottom piece and do the exact same thing. 16 minus 35 over t. So the limit as h approaches 0 of 16 minus 35 over t, so it's 16 minus 35 over t plus h, minus the original function, which is in parentheses 16 minus 35 over t, all over h. So I got to clean this up, sub in 0, take the limit, and see what that equals. All right, here goes nothing. Well, what do we got? We got 16 minus 35 over t plus h, minus 16 plus 35 over t, all over h. I got to be particular here. I got to write this in there. I don't want them to take a mark away from me for that. All right, 16 minus 16 cancels out, and we got negative 35. Let me come over here and rewrite that. Limit as h approaches 0. I'm going to get a common denominator of t times t plus h. So that first fraction I'm going to multiply by t over t, so it's negative 35t over t plus h times the t, and then plus multiply that second fraction by t plus h to get the common denominator, t plus h over t times t plus h all over h. Here we go with a lot of cleanup work here. The numerators, we're going to have negative 35t, and then we're going to have a positive 35t. That's good. That's going to drop out. And then we're also going to have plus 35 times h. So on the top, we're left with 35h all over the common denominator, t times t plus h. And that is all over h, which means we can bring that denominator of h up to the other denominator and take the limit as h approaches 0. Now the h's cancel, and remember you're taking h approaching 0, so now we can legally do that limit, and we get 35 on the top, and we get t times t plus h, but h is approaching 0, so we get t squared on the bottom. All right, so that's the derivative of the second piece of the piecewise. But we're checking the differentiability at the point where it breaks apart, which is at 5. So substitute 5 in for t. Let t equals 5 gives us 35 over 5 squared, which is 25. Reduce that down by dividing by 5, and we get 7 over 5. That is the derivative of the bottom piece at 5. The derivative of the top piece was 7/5. The two derivatives are the same. Therefore, we can put that in words, since the limit as t approaches 5 from the left of w of t is equal to the limit w prime of t, the derivative, as t approaches 5 from the right of w prime of t. Since those two derivatives are equal, therefore it is differentiable at t equals 5. Yay, done. All 14 marks. Okay, the end.